Good afternoon, Physics 30. I hope you guys are all having a good day today. So welcome to the last video of the unit. This is your last lesson for the unit on electromagnetic radiation. So what that means is that when you're done this lesson, you can finish up your EMR Chapter 2 assignment and get that handed in on Google Classroom. What that also means, this is your last mandatory video. I know, it's so sad, right? After this video, I'm going to continue making videos, and they're going to be the atomics physics lessons. Now, remember what I'd mentioned earlier is that last unit on atomic physics is optional. It's the unit that I have kind of weeded out as not being as vital as the other units. When COVID hit, we were told we had to trim down objectives and only do the mandatory or the most important ones. But because you guys, and there's some of you guys who are going to be going on to have physics-based programs in university to study physics, I wanted to make sure you had the choice to at least get exposure to that last unit if you so wanted. So if you are finished physics as of now, congratulations, you're done. I'm going to miss you guys, rock grad, all that good stuff. And if you guys are wanting to continue on to atomic physics, awesome. And then we would see you in the next video. Okie dokie. So for those of you who are finishing physics now, be prepared. Last physics lesson with Mrs. Bray before you guys graduate. And for those of you who are going on to the last unit, welcome to the last video of the last video of the chapter. There we go. All right. So, ladies and gentlemen, we've got our last topic is about de Broglie's principle. Now, this is actually kind of cool. Now, de Broglie, what he'd suggested is that if light and all other types of EMR behave like particles and can have some properties that are like particles, such as momentum, well, can't particles such as electrons and protons have some wave properties? I know, right? Crazy. So, ladies and gentlemen, so what de Broglie did is he did some experiments to see, well, could particles like electrons have a wavelength? And could they actually behave in some cases like light? So, ladies and gentlemen, and he did find that. And what this suggests, it supports the idea of wave-particle duality. Okay? So, ladies and gentlemen, what de Broglie suggested is that the wavelength of these particles, so your electrons, can be related to their momentum. Well, ladies and gentlemen, remember that our momentum of an object that has mass is equal to P equals mv. Okay? Now, also remember, we have our momentum, or P, of a wave. Okay? Remember that wave momentum is equal to h divided by lambda. So your Planck's constant divided by your wavelength. Well, what we can do is we can equate these p's, so P equals P, so therefore mv could equal our Planck's constant divided by wavelength. Okay, so taking that from there and taking that from there. So what we can then do is we can rearrange this guy in order to get an equation to calculate the wavelength. Okay, so therefore our lambda is going to equal your Planck's constant divided by your mv. Ladies and gentlemen, This is not on your data sheet. So what I would do right now, pause the video, grab your data sheet, and write that guy on there. Because once again, we're only doing assignments now. Is I would just write that on there. And when you come up to a de Broglie question on your assignment, just use that equation. If we were having exams or diplomas or what have you, you would need to memorize this concept and be able to derive this equation yourself. Okay. Okay. So in the meantime, though, just write down that equation. So once again, ladies and gentlemen, P is our momentum, kilogram meters per second. M is your mass in kilograms. V is your velocity in meters per second. Lambda, wavelength in meters. H is your Planck's constant, units on your data sheet. Okay, so joule seconds. Sounds good? All right. Now, what is often called, now our wavelength of a particle, it's often called the de Broglie wavelength. So if you ever see a question that says, what is the de Broglie wavelength of an electron or what have you, then the equation that we just wrote down, that's going to be your go-to. Now, well, how could we actually experiment or demonstrate this? Because we can't just say, oh, well, they have wave properties and use this equation. No, there has to be experimental data to support this. And there is. So what de Broglie did, Thomson, it was Thomson who did this. Thomson demonstrated that electrons can be diffracted, very, very similar to Young's double slit experiment. So using a thin gold metal foil or use a crystal to get an interference pattern. Well, that's the property of waves, guys. And Thomson did this with a beam of electrons. So the fact that you can have electrons that are going to be diffracting and having interference patterns, that is your evidence. Okay. So once again, supporting wave-particle duality. So this is just a cool picture showing that. I really like this one here. You got your beam of electrons, you've got your foil, and look at this. These particles are diffracting, and when you look at the screen, you get an interference pattern. Isn't that cool? I like that. And then this here is just your image for a crystal. You've got here your little crystal surfaces, your little atoms, and your electrons come in there, be diffracted. And you're going to get, reflected, and you're going to get your detector over here. Okay, so just how they would use the crystal, but still going to get your diffraction pattern. It's awesome. Awesome. All right. So ladies and gentlemen, that's the theory. And we've got 2 questions. This is actually one of our shorter videos. Like some of the last ones are like an hour. I think this one's going to be no more than 20 minutes by the time I'm done filming. Maybe 15. All right, so ladies and gentlemen, an electron has this mass. Surprise, surprise, that's on your data sheet. So our mass is 9.11 times 10 to the power of negative 31 kilograms. Calculate the de Broglie wavelength. Now that is our key, ladies and gentlemen. We say the de Broglie wavelength. That tells you automatically you're going to use that calculation or that equation, that I just gave you. Okay. For an electron with a speed of this guy. So a speed of 2.15 times 10 to the power of 6 meters per second. Okay. Well, remember that P equals mv. Remember that P equals h divided by lambda, just like we did in the previous question. And then you can have our mv is equal to h divided by lambda. Just like we did in the previous question. Assuming we would have diplomas, you'd actually have to do this But because we don't, you can just take this equation that I'm writing down right now, that we just wrote down earlier, just write that down. Okay, unless you want to do all this. So I'm going to take this equation here, and I'm going to plonk in my values. So H is my Planck's constant. Gotta use joule seconds, guys. I mean, look at the units. Okay, joule seconds. Please don't use electron volts. It makes me sad. Okay, use electron volts in the wrong place. So 6.63 times 10 to the power of negative 34 joule seconds. That's your Planck's constant. Now our mass of the electron, 9.11 times 10 to the power of negative 31 kilograms, and 2.15 times 10 to the power of 6 meters per second. All right, so you take this and plonk that into your calculator. 3, 3, 8, 4, 9, 8, times 10 to the negative 10 meters. With your sig digs, 3.38 times 10 to the power of negative 10 meters. Sounds good? Cool. So that's a pretty straightforward question. Let's look at question number 2. So our last question, my email's been going crazy today. You know, the binging of the email alert in the background there. So calculate the wavelength of an electron. Ladies and gentlemen, the second you see the wavelength of an electron, which when you first start hearing that, it's just like, how is this possible? Wavelength of a particle. Well, de Broglie. Wave-particle duality, guys. So the second you see that phrase, it means you're going to use your de Broglie wavelength principle. Okay? With a kinetic energy of this many joules. Okay, now this is our challenge. So we have our EK of 3.10 times 10 to the negative 16 joules. Well, we've been asked to calculate the de Broglie wavelength. Well, our equation for a de Broglie wavelength, as we've already derived, is our H over mv. We've got nothing with kinetic energy there. Well, what are we going to do? Are we hopelessly lost? No, you're fine. We can use another equation. What is it? What's my first step going to be? Good, use the kinetic energy to get your speed. So, ladies and gentlemen, what I am first going to need to do is I'm going to have to use my EK equals 1/2 mv squared and just rearrange that to give my v. Ladies and gentlemen, you absolutely cannot use our E equals hc over lambda because this is for photons only. Okay, that's for photons only. If you use this with de Broglie, you are going to have a very sad Mrs. Bray. Okay, you can only use this guy with photons. You cannot use this with de Broglie. Okay, now because electrons are particle, they have a resting mass. We can use EK equals 1/2 mv squared. We use that to get our v, then we use this guy for de Broglie. Okay. Now, if this was on an exam and we were still in class, I would jump around and wave and do something equally ridiculous, but my silliness has to be limited to the camera. All right. So, ladies and gentlemen, let us calculate our speed with our kinetic energy. So, ladies and gentlemen, you guys already know how to rearrange this equation. Our V is going to equal our 2 times our EK divided by the mass, square root that. 2 times our EK of our 3.10 times 10 to the power of negative 16. Divide that by the mass of an electron already given to you, so 9.11 times 10 to the power of negative 31 kilograms. root the lot, put it in your calculator properly, please. And you're going to wind up with a speed of 2.6087 times 10 to the power of -7. -7. Get out of there, negative sign. There we go. Meters per second. Now that we've done that first step, now we can use de Broglie. Okay, I'm going to draw a line here just to kind of separate that bit. Okay, so now what we're going to do is we're going to take our speed. These two are constants. We're good there. And we're going to plonk it in. Okay, so lambda is equal to, now Planck's constant, get this in joules, gotta use joule seconds. Okay, so 6.63 times 10 to the power of -34 as a decimal, and we divide that by our mass of 9.11 times 10 to the power of -31. Multiply that. I am running out of space. I'll put that line back after. Okay, multiplied by our speed of 2.6 times 10 to the power of 7. There we go. Put that line back. Okay, plonk that into your calculator. Put it in properly, please, ladies and gentlemen. And once you've done that, you're going to wind up with your lambda with sig digs of 2.79 times 10 to the power of -11 meters. Sounds good? Ladies and gentlemen, that is de Broglie. I know. I can't believe we're already finished the unit. It is bonkers. So, ladies and gentlemen, we've got some practice problems here. Give one of two of those a try and finish up that last assignment of the unit. For those of you who this is your last video and are finishing physics now, congratulations. For those of you who are finishing physics, in the next, after we finish atomic physics, we'll see you guys in the next one. Ladies and gentlemen, no fires, injuries, or explosions. And sign up on Google Meet if you guys have questions. We'll talk to y'all later. Bye. Now I can't turn it off. There we go. See you later, guys.